Yesterday, I looked up at the stars, and what struck me was a little set of stars. It looked like a set of stars that were moving in line, and those, of course, being satellites. And I thought to myself, this is really part of this whole new space era, where we suddenly look up at the stars and we see satellites that we couldn't see before, just, I would say, 5-10 years ago. They were not part of what we could see. And that is actually what we're talking about today, this new way of doing space technology. Today we're talking about software in space technology and how software and the approach to software is now changing how space tech is looking and how it's made and what's it's all about. And in the studio or on an online link, I have with us Andreas Stren. Welcome to you, Andreas.
Thank you.
And I have you down as the lecturer of aerospace engineering program at the University of Applied Sciences in Wiener Neustadt. And with us also, we have Alexander Spaniol, who is a radio frequency engineer here at Terma, of course, in the space department. Welcome to you, Alexander.
Thank you. Hello.
I want to start out. I warned you about this before starting the recording. So I want to start out by asking you, how have the approach to software, how has that changed over, well, let's say the last 20 years from, well, I was just about to say the first missions, that's a little bit more than 20 years ago, but how has software in space tech changed, Andreas?
Yeah, it changed mainly that more and more tasks are taken over by the software itself that were formerly executed by analog parts, for example. And together with this, also not only the complexity of the software has risen, but also the possibilities we can have. For example, that we update something in the software during the mission. It isn't that we can go up there and change the hardware, for example, and the satellite. That's pretty hard.
But just for me to understand, can you give an example of what that could be?
Mm-hmm. For example, I think we have also time to get a little bit deeper later on. For example, there is something called field programmable arrays. They can be updated with a software, and internally they change their configuration. So the same part has another function just by software update. That is an example. Right?
Okay, and how does it really work? Because you still need some hardware, Alexander. How does it work now?
Good. I think Andreas already got the point quite well. So with this new space era, this prioritization of the space sector, but we can clearly see that we need new products, another product with a specific use case that somehow must be such a platform with general purpose and so on. And that cannot be done with old hardware that is very restrictive to one specific use case. We need new ways. And nowadays we often talk here about this software-defined everything, or a special thing for that is this software-defined architectures. And that is one of the developments where we can see that the market goes where customer requests us to deliver on this. So having, for example, this FPGA, Andreas already mentioned, is we have software with which we can program, for example, this hardware piece. And doing this, we can do many different things just by using software or writing the software for it, and not just changing hardware, doing some physical work. It's all done digitally.
But what? How do you create the hardware then? Because you still need hardware to run the software on.
That's the specific thing of FPGAs. It's how should I say, very very complex thing. But I think that Andreas can talk a little bit about that. He had some experience with that. I'm more like the user bit there. And Andreas already did also programming directly on the JS.
Well, we about this we speak on a level where it is very close to the hardware. So it's also called embedded programming, where we use integrated circuits that have a certain task or a certain function. And this new programmable arrays can change their the position or state of transistors within the computer chip just by defining it by software. So that's actually a hardware change due to a program that is uploaded.
And maybe just to get the point to cutting edge software technologies, how they influence our space industry today. A very well known application for that is, for example, the software defined radio, which is like part of software defined architectures, where we combine this reconfigurable hardware with very powerful software, and that's the key point. And why it works out. That gives us many advantages. We have very flexible systems that can be used for several different things just by changing the software. We have reductions in costs, because we are no longer dependent on a specific hardware that can just be used for one specific case. We have a programmable hardware, which we can control via software. And what we actually then do is we program our software to make the thing doing that what we want to do it.
And what sorts of requirements is now set to the hardware on board?
On board of the satellite, or let's say on an application. Regarding the hardware, or if we're now talking about software defined radios or software defined radios that are on the satellite, then we have to think about how we can withstand with this hardware, this reconfigurable hardware, the atmosphere. We have a very harsh environment. We have radiation. We have high temperature fluctuations. And we have to manage that this little piece of hardware that we have that survives this atmosphere in order to get our software running on that. And Andreas, you can for sure maybe speak about what this hardware needs to withstand there out in the orbit.
Well, space is environmentally difficult to handle. Not only that we can just send a service team, but also often the operation time of such satellites can hit decades without actually maintenance. And therefore the systems that we can if we can control the systems easier by uploading for a new program, for example, the satellite itself can be maintained. And specifically on the environment, we have radiation. That's the most important impact for digital devices. But we also have like thermal fluctuations. Then we need to consider power needs. We need to consider that the power configuration must survive the radiation and temperature, and the combination of these requirements is hard to handle in terms of also how do subsystems speak to each other. For example, if a subsystem has a more capable software and chip, for example, then it can also act individually without being restricted to one or two commands that needs to be from a central computer. So there is also another advantage that evolves out of it, that each subsystem can handle itself more easily if the capability of the software rises. Yeah.
I was just thinking, when you have larger possibilities with software, you also require, say, processing power, you require more powerful systems on board. Is that a problem, or how does this new, I'm saying new, how old is it? The software first kind of approach?
The software-defined radio, just to maybe to get the answer for the last question, software-defined architecture, software-defined radio, and so on, that's already, it's not new. We have that for, let's say, several years or decades, yeah. But the actual application to run these systems with advantages over hardware-defined systems, there the test is now coming or can be used. And therefore, we nowadays see the applications for that, what was already developed in the past. So this idea already is quite old, let's say, yeah.
And what does it set of requirements to the build of, say, the satellite? Does it require a larger power output, or?
Yes, definitely. I can go on this one. Definitely a larger power need, yeah, and it must be secured. So power is the most important thing for a satellite. If the power goes out, your mission is lost. Yeah. Mm-hmm. And the second thing is communication, to actually interact with the satellite, and everything else comes afterwards. Yeah. So the and also there you already see that that the control of power management and the control of communication is the most important to improve and make fail safe. And therefore this more powerful systems, as for example an FPGA, then is capable of more redundancy, I would say. For example, if the integrated circuit has a problem, we can reconfigure it, and then the problem is solved. So the increasing requirements go hand in hand with increasing redundancy and also to fail safe, I would say. Yeah.
When we're looking at the mission planning prior to a space mission, what does it mean now that we have different possibilities just by, I'm saying just by, I know it's harder than it probably seems, but just by updating the software, what does that mean to, I'm guessing like it means something to the lifespan of the satellite, or?
The software-defined architectures, when we specifically look at the mission planning, there you can see that software has transformed how space missions are planned. The software make them more agile, yeah? Data-driven, and of course also efficient. And specifically the last point you have mentioned about the lifespan, since with software, or when we have this software-defined approach, or maybe also software-defined satellite, where most of the systems rely as much as possible on software. And we have the great possibility that we can react on certain events that happen in the orbit, can happen, and we can update and change our system to what we are required to. If we have a problem, for example, with the communication on that specific frequency, or with that specific modulation type and so on, we are actually able, by updating the software, to change that. And that, for example, was in the past not possible.
In the past, would you suddenly lose communication to a satellite, and then that mission is just gone?
Yeah, for sure. So if you, for example, cannot change the frequency because it's just programmed into your hardware modem, then the mission can be lost. Yeah.
I can also tell about the process to build a mission changed. Okay, so when you speak about mission planning, it's not only the moment the satellite is up there, so also the approach how to design the actual mission has changed. An example would be that the mission requirements define a task that the satellite has to do, made Earth observation, communication, name it. And during the design process, you always had to consider, okay, which ground station am I using, or which network do I have to build an own ground station?
Gotcha.
And for example, is this ground station? If you build a ground station on your own, do you only tune it on that specific communication protocol? And with the SDR technology, we can actually, as space engineers, we can actually reduce these requirements and concentrate more on the actual mission of the satellite. Because we have more versatility. Yeah.
Does that, and you can also reserve more resource, I'm guessing, to the actual goal of the satellite. Do you think this? Yes, Alexander.
Maybe just a point to that. Speaking about resources and so on, having everything in software allows us to, or for sure, also do automated mission design. So we have software-driven systems that help us on automating many aspects of the mission design. How we react on how we change the orbit, how we plan to do our trajectory, how do we configure our spacecraft, and especially also maybe regarding risk management. And
so basically setting up that if this event happens, then do this automatically.
Yes, that's possible with software. So we can automate processes where we don't need this, let's say, human power or a human that decides how to do it. That can be automated. And that for sure, since you mentioned it, saves resources in our time.
And just, I know that this is not like, it's not necessarily or it's probably something fairly new, but this automation of processes, is that also a door into autonomous decision making at the satellite itself?
Is it? Nowadays, everyone already heard it for sure. That is done by AI, so artificial intelligence, and also for machine learning, And with this, we are increasingly used to automate this task. So actually, we have an onboard AI that makes the decision making for us, and at the point where it is required. If we human need to do the decision making for the satellite up there, we really have a problem, because we need to get a communication window, because the satellite now needs to be above a certain point above the Earth, where we have to link with the ground station, and then we have to tell via an uplink the satellite what he needs to do, and we can only do that when we receive the information prior.
I think that problem is something that's very obvious to people working in the space industry, but it's something that it kind of baffles me every time. The fact that you have to wait for your satellite to come back around to orbit Earth, and then once it's maybe not directly above, but it's when it's within that kind of visible window, or what you call it, then you can say something.
Yes.
Yeah, when it's within the horizon, right? And then when it's outside again, well, you have to wait.
Yes.
For what? How long time does it take? I don't know. Well, it depends.
Here it also depends on your mission or communication architecture. There are several types of that, and maybe you've at some point heard geostationary. That would be a different approach to swarms of satellites that are very close to Earth, and therefore the orbit design also defines your communication architecture. So if I, for example, want to have communication with a satellite that is outside a line of sight, I either need another ground station that I connect to, or we can, for example, relay the signal via a different satellite and make a sort of chain.
But for that, you would require a constellation, so you need more than one satellite.
Yeah, so that's what SpaceX would be able to do with their
Yes, they have an interconnected close range communication in between each satellite, and if you take thousands of them, you can reach satellite number 500 at any time, because it relays over several others.
And that is controlled using AI. That cannot be done by humans.
Okay.
Possible.
Yeah. So that linking, and it's actually, I'm guessing that's not even hard AI. That's what Google Maps solved that kind of AI a long time ago, and even that algorithm is probably it's probably from their 40s or something like that. So that's like just the shortest distance kind of algorithm, right?
But also it raises respect for the people who built this in the first place.
It does absolutely. Yeah. I'm can't but think, but. In your opinion, do you think that this push for software-defined radio, is that a natural thing? Is that a natural development? Would it have happened anyway? Or is that the result of more private actors entering the space market, where you have I'm guessing that Elon Musk and Jeff Bezos, they more or less have unlimited resource, but let's just say that it's not unlimited resource. Someone, you can't just keep on spending. Does this push come from there mostly, or would it have happened anyway?
I think there are two reasons for that. One is for sure this development to this new space era with the privatization and so on, where we definitely look more into how much money we actually spend on the system. That is one point. And the other point, I think, is we are always interested in advancing our technologies. And of course, if we have a technology that works for a specific use case, and we have the opportunity to advance it in a way that it works for several use cases just by reconfiguring it, then we for sure do that. And we also would have done it in the past, but there the tech wasn't here. But nowadays, with the technology we have, with the FPGA, networks on the ground with high speeds, low latency, we are now finally really able to get this technology working. And that is, from my point of view, the second point, where we now have this breakthrough and this push to software define everything.
I'm also guessing that these missions that are not near Earth, but the deep space missions, they're actually only meaningful if you have some sort of autonomous decision making at the satellite, because you can't wait for 2 days to answer.
In most cases, we just do.
You just wait. Yeah, you just wait. So you send out the signal to whatever satellite that's on its way out of the, and then you just wait.
Yes. If you're also talking about new space here, like in old space or big space, they're not really terms, but to think about it was like, yes, if you want to call a satellite that's 40 light minutes away, the answer will take 80 minutes.
Yeah, because you need the communication to first get out there. You'll have it do its job and then send back that confirmed or.
Yes, with the first few Mars rovers, it was exactly like that. That someone in the operation room, for example, sees a stone on the surface, tries to navigate around, makes an input, and 40 minutes later, there was like, oh, okay, did I hit it or did I miss it? Yeah.
Yeah. Whereas that now it will just drive around.
Yes, and we can watch the decisions afterwards and make adjustments to them.
Yeah, and teach them new things. How do we want you to react next time?
Yes, exactly.
And that, of course, both goes for Mars rovers, which is really cool, but also satellites and telescopes and everything. I'm wondering, what do you see coming ahead? What's on the horizon development-wise in software-defined, not software-defined radio, but software and tech? And software then we'll deep dive into software-defined radio in the next episode.
I think that this the next big thing, or one application for having this software-defined approach is now this big term of virtualization, meaning that we have a small hardware, like, for example, we already talked about it several times, our software-defined radio device, which gets the analog waveform of the signal I receive from a satellite, and then I more or less directly digitize it, and then I already have it in the digital domain. So I virtualized it. And using that, and by having it in the, let's say, for example, hosted in the cloud, we can access this information we got from the satellite, say, more or less from everywhere. And that's the big topic I see, or we see, where we have development going to this specific application for this software-based systems.
Also, developments, I've seen that already ongoing, and if we speak about the future, is, for example, the virtualization connected to the capability of the satellite, that the satellite can interpret data on its own. So in the past, there was always, okay, we get the data, we get it down to Earth, we take a look at it and interpret it. And all these processes can be outsourced to the satellite itself, so that actually the post-processing can be handled on the satellite itself before even the data reaches Earth. Where it is implemented already is wildfire detection, for example. That the image the satellite takes can be processed on board, and if it detects a wildfire, can give a warning signal, even though the data hasn't even arrived at any human interface.
Yeah, I was just about to say, what are the practical usages of that? Why would you want to throw the processing power up in the air, so to say, or out up in space, where you can't upgrade the processor, or you can't upgrade the hardware at all? So why would you want to do that? What's the benefit?
There are two that I can speak of. Like wildfires are already mentioned. Many of these applications concentrate on image observation. For example, Earth observation is like the top topic. Yeah, but also, for example, if you want to land something on another celestial body, as we said, the latency of communication signal leaves no time to actually react something that happens during a landing. So the interpretation of data from the spacecraft itself to react to the actual situation right now, that is one of the major points that are really improved by now and will improve.
Maybe also something about the observation thing in this Wildfire, why does throw up the processing power of this up to the satellite. You also have to think that these images are resolutional images, and they have a vast amount of data, and we have to really transfer this data down to Earth and then process it there. And that really can be challenging with very high data rates, very high bandwidths. We may also have problems with adjacent signals that influence our signal quality, and we may, for example, not be able to get a link or get the full image that we would require in order to further process it on Earth. And if we directly do that on the satellite and then just give the result down to Earth, we are only speaking of hundreds or thousands, whatever, just house numbers. What we have to send down to Earth, for example, in that case.
So it's basically the exact same problem as when I upload this video to YouTube. This is probably going to be like a 50 gigabyte video. So if my connection is just a little bit off, it will take forever. or crash.
Mm-hmm.
And that's the same thing.
Here, yeah, and we are speaking here of data rate 1 gigabit, for example, let's say 100 Mbit. Yeah? But with the satellite link, I don't know, if you have a high data rate modem, you may be able to achieve 100 Mbit per second. Yeah? But normally we speak about 8 Mbit, let's see. Yeah? And now you will really have to wait a long time to upload gigabytes. Yeah.
Our time is up, but in the next episode, we'll talk more into this software. We'll talk more about software-defined radio, more deep dive into that particular type. And I think that's going to be very exciting as well. Also, probably very geeky, just a warning sign for everyone out there. But I'm looking forward to it anyway. Andreas Stren and Alexander Spaniol, thank you so much for joining this conversation. And I look forward to talking to you again in the next episode.
Thank you.
Thank you.
And of course, to you listeners out there, thank you so much for joining this conversation. And if you have any questions or any topics that you want us to dive into, just reach out to us on podcast@terma.com. That was podcast@terma.com. And of course, if you like this episode and want more of it, just hit that subscribe button, and a little bell notification always helps a little bit. And of course, share it with your friends and colleagues or whoever might be interested as well. That really helps us quite a lot in spreading the word and spreading the knowledge, which is obviously the point of us talking here at all. So I think with that, all I have left to say is thank you so much for listening.
Nice to be here. Thanks.
Bye.